This lesson concerns the trigonometric form of complex numbers. We're going to assume that you've had experience with complex numbers from your algebra class. We assume that you understand the form of a complex number, how to add and subtract, multiply and divide those complex numbers. If you have not had experience with complex numbers, you probably need to check out the videos concerning complex numbers from college algebra and do some review there. Make sure that you have some background. Now, I will do a quick review about some of the basic concepts of complex numbers, but I won't be able to cover everything that you probably need to understand before you go into the trig form. Let's take a look at what we mean by the standard form of a complex number. A complex number has the standard form a plus bi, where a is called the real part and b is called the imaginary part. The standard form is also called the rectangular form, and you'll see a reason for that in a second when we talk about graphing complex numbers. Just to get you an idea, a plus bi are things like 2 plus 3i, 1/2 minus 2/3 i, the square root of 5 plus 4i, etc., etc. 3i by itself, that would be a complex number. So these are the things that we're talking about, a complex number in standard form. Now, a is called the real part. That means this part right here. In this case, 2 would be the real part, 1/2 would be the real part, etc. b, which is the coefficient of I, is called the imaginary part. So here the imaginary part is 3. Here the imaginary part is -2/3. So you do need a basic understanding of these complex numbers in standard form. Now, the reason we call them rectangular form is because of the way we graph these complex numbers. If you're graphing complex numbers, you label the horizontal axis as the real axis. That would be like the x-axis. We're going to call the real axis. And the vertical axis, or the y-axis that you're used to, is the imaginary axis. To graph a plus bi, use the ordered pair AB as the endpoint of a vector with initial point at the origin. Now notice this ordered pair. A, the real part of your ordered pair, is the first coordinate, like x, and the imaginary part, B, is like the y value. Now we're going to take a look at an example. Graph the complex numbers 3 minus 2i and -5 minus 4i. Okay, let's look at this first complex number. We're going to look at the ordered pair where we take the real part, 3, as our first coordinate, and the imaginary part, -2, now be sure you get the sign on that, as the second coordinate. So we're just going to graph the number, the ordered pair, 3, 1, 2, 3, -2, locate that point. Now we will indicate a vector from the origin out to that terminal point. This vector represents the graph of this complex number 3 minus 2i. Okay, now let's graph this one. The ordered pair we will use, the real part is -5, the imaginary part is -4. So let's locate that point, -5, 1, 2, 3, 4, 5, -4. Locate the point. Now remember, from the origin, we're going to go out to that point. So this second vector right here would represent the graph of -5 minus 4i. Now, since the graph of a complex number is a directed line segment, complex numbers are vectors and may be treated like vectors. We're going to see how this works in this next example. Find the sum of the complex numbers 3 minus 2i and -5 minus 4i. Graph both numbers and their sum, and you'll notice I've put here resultant. I'll show you why I've used that terminology. Again, this first complex number is 3, -2. So we had graphed that, I believe. I think that's the same one I used a minute ago. So there's the first one. The second is represented by negative 5, negative 4. Okay, so we're going to come down here. Okay, now it says find the sum. 3 minus 2i plus negative 5 minus 4i. If you recall from algebra, you add the real parts. 3 and a negative 5 added together gives me negative 2. Then you add the imaginary parts. Negative 2i minus 4i. If we add those, we get negative 6i. Now, if I'm going to graph this sum, the ordered pair I use, the real part negative 2 is my first coordinate. The imaginary part negative 6 is my second. So let's go negative 2, 2, 4, 6. So the sum, the resultant, I'm going to call it, is right there. Now what I want you to notice, if I completed the parallelogram like we learned the parallelogram rule for vectors, notice that this diagonal of our parallelogram is the same thing as the sum of our two complex numbers. So adding two complex numbers is just like adding two vectors. We can get that sum geometrically by finding the resultant vector from that parallelogram rule. Now that you've had sort of a quick review of complex numbers and some of their characteristics, we're ready to start talking about what we call the trig form of these complex numbers. You might have been asking, what does all this have to do with trigonometry? So let's take a look at how we're going to convert from this standard form over to the trig form. The trig form of complex numbers. Consider the complex number x plus yi with magnitude r and direction theta. Now, I want you to treat this as the x-axis and the y-axis. And I didn't want to put all the little squares on here to clutter up our graph. The complex number x plus yi would be represented by a vector with an endpoint at the real part for the first coordinate and this for the second. So this point right here would be the graph of this ordered pair xy. Okay, so this is going to be the ordered pair xy. Of course, when we start at the origin and we go out to that point, we will have created a vector with a magnitude that we're going to call r, and it will have a direction from horizontal of this angle theta, rotating up here. Okay? Now, here's what I want you to look at. If from this endpoint I drop a perpendicular down to this x-axis, since I'm right underneath this point whose coordinates are x, y, I know from the origin out to here is the same thing as x, isn't it? My horizontal distance is the same as this first coordinate. And then from here up to here is the same thing as whatever this y coordinate is. If you notice our right triangle, you can see that the sine of theta is y over r, and the cosine of theta is x over r. Okay? Now, we can take this and multiply both sides by r. R's cancel here. We have y equals r sine theta. Doing the same thing over here, multiplying both sides by r and canceling over here. We have x equals r cosine theta. Now, let's come back to this standard form. X plus yi. In place of x, I'm going to put what x is equal here. In place of x, we can put r cosine theta plus. Here we have y, and we're going to replace y with what it's equal to. So r sine theta times I. Now, usually, so that we don't get this all confused and mixed up, we write this way. R cosine theta plus r times I sine theta. Since we have r in both terms, very often we will factor that out and write r times the cosine of theta plus I times the sine of theta. And this is what we call the trig form. Now, you will find out in a second that we will also have an abbreviation for that form, which is fairly nice. while we're here on this screen, because we're going to need this a little bit later, I want to call your attention back to your triangle here, and notice, since this is a right triangle, that r squared is going to equal x squared plus y squared, which means r is the square root of the quantity x squared plus y squared. So we can take the real part and the imaginary part, square those, add them together, take the square root, and we have the magnitude of this complex number. Also notice that the tangent of angle theta is y over x. We're going to be coming back and looking at these formulas a little bit later, but I wanted to let you see where this trig form sort of comes from before we look at the formal definition. The trigonometric form of complex numbers, and by the way, we usually abbreviate that and just say the trig form. We always get lazy, don't we, with things like that. The standard complex number x plus yi with magnitude r and direction theta has the trigonometric form r times the cosine of theta plus I times the sine of theta. This is also called the polar form of the complex number and is sometimes abbreviated as r CIS theta. This gets really tedious to have to write this out every time. Since r can be factored out, you'll notice the r out here, but notice this theta is the same value. So instead of writing cosine theta plus I sine theta, we abbreviate CIS theta. Stands for cosine theta plus I sine theta. So you'll find that I'll write this quite often just to save space and because it's easy, but you need to always remember this is what that CIS theta means. Having looked at this definition, let's also look at the components of the trig form. The r, which is the magnitude, is also called the modulus, or the absolute value of the complex number x plus yi, and it's always positive. If you remember when we went back to find the r based on the way we set up this trigonometric form, r was the square root of x squared plus y squared, so it has to be positive. Now, theta, the angle, the direction if you will, is called the argument of the complex number. The argument is usually given as an angle from the interval 0 degrees to 360 degrees. But other values are possible. Thus, the argument is not unique. Let me place this graph back up here. If I have this complex number represented by this vector, I can give the direction by giving from horizontal up to here. Keep in mind that I could have done a complete rotation and have come back up here. And so let's say if this had been a 30-degree angle, 360 plus 30 would have also been an acceptable angle. Now, if I had wanted to, I could have rotated in a clockwise direction and have given a negative angle, but that's usually not something that we do. Notice it says it's usually given as an angle from 0 degrees to 360 degrees. So we usually give a positive angle here, and we don't consider rotations around. Now, you will sometimes also see this thing written with radians rather than degrees, which is okay. I think for the most part here I've worked with degrees, but I think I may have put in an example or two with radians. I want to again call your attention to the conversion formulas. These become very important. Remember, we derived x is equal to r cosine theta, y is equal to r sine theta. To get r, we take the square root of x squared plus y squared. The tangent of theta is y over x as long as x is not 0. We can't have a 0 down here. Basically, what we do with these formulas is we will convert back. If we have r times cosine theta, that gives us x. If we have r times sine theta, that gives us y. If, on the other hand, we're trying to go from the standard form to the trig form, we can find r by taking the square root of x squared plus y squared, and we can figure out the angle theta by using this tangent. Now, I'm going to have to mention to you as we do examples, you have to be careful with this angle, and I'll show you why. as we look at some examples. Okay, well, let's do this first one. Convert 3 times the cosine of 30 degrees plus I times the sine of 30 degrees from trig form to standard form. Actually, this turns out to be pretty simple. Now, you'll notice the r, it's like r times cosine theta plus I sine theta. This 3, however, distributes across this plus sign, doesn't it? So I'm going to just write that down for emphasis right now. I have 3 times the cosine of 30 degrees plus 3i times the sine of 30 degrees here, just distributing my 3 across here. Now, anytime that you have a special angle like 30 degrees, 60 degrees, 45 degrees, etc., you want to give exact values. If these angles are not some of your special angles, then you'll simply go to the calculator to do that. Now, I'm sure most of you have gotten this down pretty good by now, but I'll just remind you on your 30-60 triangle, the way that thing is labeled. So the cosine of 30 degrees is square root 3 over 2. So I have 3 times the square root of 3 over 2 here, plus 3i times the sine of 30 degrees, of course, is 1/2. Now, we want this in standard form, which is the a plus bi form, so we're going to multiply this and write 3 times the square root of 3 over 2, plus, I've got 3 times 1/2 is 3 halves I. So my a is 3 square root 3 over 2, my b is 3 halves, and that's in that standard form, a plus bi. The real part here, the imaginary part, 3 halves. Convert 4 CIS 120 degrees from trig form to standard form. Now, this is written in that compact abbreviated format, but let's just remember that's an abbreviation. 4 times the CIS, C for cosine, 120 degrees, and then you need your plus sign, the I times the sine of 120 degrees, okay? And again, the 4 will distribute here. Now, I have 4 times the cosine of 120 plus 4i times the sine of 120 degrees. Now, if you think about your 120 degrees, that's going to be over here in the second quadrant, isn't it? The reference angle is 60 degrees, recall. So, in the second quadrant, the sine is positive and the cosine is what? It's negative. So again, thinking about your 30-60 triangle, your 1, 2 square root 3, the cosine of 120 is going to be just like the cosine of the reference 60, which is 1/2, except in the second quadrant it's negative. So I have 4 times negative 1/2 here, plus 4i. The sine of 120 is going to be just like the sine of its reference. Sine of 60 is square root 3 over 2. In the second quadrant, that's still positive, square root 3 over 2. Now let's multiply this out. 4 times negative 1/2 is negative 2. Plus, when I do 4 times square root 3 over 2, the 2 is going to cancel with the 4. And I'll have 2 times the square root of 3 times I. So again, this is my a plus bi form. A is negative 2. And b is 2 square root 3 times I. Now, let's look at this next one, which is also converting from trig form to standard form. Convert 7 CIS 297 degrees. Now, you'll notice right away, 297 degrees is not going to give you a special angle as a reference angle. So here, we're just going to simply use the calculator. Again, recall, this is an abbreviation for 7 times the cosine of 297 degrees plus I times the sine of 297 degrees. And again, we can distribute that 7. Now, you will probably get to the point where you don't write all of this out every time because you just think about what you need to do, but I just want to be sure for emphasis that we don't leave anything out. Now, as we go to our calculator, be sure that you have your calculator set for degrees here, because we are working in degrees. If you're set for radians, you're going to get an incorrect solution when you put that thing in. So I'm going to start here and multiply 7 times the cosine of 297 degrees. Okay, now of course you're going to get quite a few decimal places, and I do not know of a set thing other than if we're given degrees here, you may want to consider, we've normally considered that to be 2 significant digits. I'm going to kind of stick with that, and so I've got a 3.2 here. Actually it's saying like 3.1779, etc., but I'm going to just keep 2 significant digits here. Okay, so I have 3.2 plus. Now here I'm going to go ahead and multiply 7 times the sine of 297, and I'm getting a negative, so negative 6.2 if I round off to 2 significant digits times my I. Let me rewrite that without the parentheses. 3.2 minus 6.2i is my a plus bi form. I hope what you're seeing here is that converting from the trig form to the standard form is really not all that difficult, because you're simply going to be finding a sine and a cosine of a particular angle and putting that in. And again, I caution you, if it's a special angle or it has a special angle as a reference, you want to give the exact value on that thing. Now, we're going to look at going the other direction. Now, this one takes a little bit more thought and calculation sometimes to get to the right place. Let's take a look at this next example. Convert 1 plus the square root of 3i from standard to trig form. Now, let's think about if this is standard form. We can think about the ordered pair 1 square root 3, the real part, the imaginary part, being x and y. Recall from your conversion formulas that r is the square root of x squared plus y squared. So we simply need to insert our x and y here to find r. X is 1, so 1 squared is 1, plus y squared. If I square the square root of 3, I get 3. So I have the square root of 4, which is 2. Now, finding r is not going to be difficult, because once we know x and y, we know the r. Now, let's recall that where this all is related to is the fact that if I graph this ordered pair, if x is 1 and y is the square root of 3, that's a little bit more than 1, I get a vector coming up here. If x and y are both positive, this vector is going to end up in the first quadrant, and so I need this angle up from horizontal. Remember that one of the conversion formulas said that the tangent of theta is y over x. So for this particular problem, my y value is square root 3, my x value is 1. Okay? So those numbers should be ringing a bell for you. If you have a 30-60 triangle, okay, which angle has a tangent square root 3 over 1? Well, that would be the 60-degree angle, wouldn't it? So theta is 60 degrees. It's in quadrant 1, has a tangent of square root 3 over 1. Now that I know r and I know theta, 1 plus the square root of 3i is r, which is 2, times the cosine of theta, that's 60 degrees, plus I times the sine of theta, which is also 60 degrees, or if you prefer the compact form, 2 CIS 60 degrees. Okay? Now that one was pretty simple because we didn't have to worry too much about our angle. We knew we were in the first quadrant. Let's look at another one. Convert negative 4 from standard to trig form. And I've given you a hint here. Negative 4 is the same thing as negative 4 plus 0i. So it is a complex number. In this form, you can see that your ordered pair that would be associated with that number is negative 4, 0. Think about if you graph that. Negative 4, 0. Our vector is going to be going from the origin to the left on the x-axis. Okay? Now, let's find r. r is the square root of x squared plus y squared. I remind you of that. So let's see, if I square x, if I square negative 4, I get 16. If I square y, I get 0. So I just have the square root of 16, which is 4. Now, what about theta? Can I say that the tangent of theta is y over x? Well, I can, right? 0 over negative 4 is 0. Well, what's theta? Well, 0 degrees has a tangent of 0, but does 0 degrees make sense? If we go a distance of 4 and we don't rotate in, we're coming out this way. This one is not 0 degrees, even though the tangent is 0, and that might be our first choice. What we have to understand is from the graph we know that we would go from this direction around to here. So actually what theta is 180 degrees. We have to go across and be heading out this direction. Okay? So this is what I was talking about being careful when you assign the value to theta. Make sure that your theta makes sense if you think about the graph of your complex number. So negative 4 in trig or polar form is r, which is 4, CIS 180 degrees. This next example is also sort of a special case. Convert 2i from standard to trig form. Well, let's think about 2i. 0 plus 2i. That puts it in sort of that standard form that we're used to. So in this case, our ordered pair is 0, 2. Okay, well we know r is going to be the square root of x squared plus y squared. So r is the square root of 0 plus 4. Of course, the square root of 4 is 2, so we know r. Can I say the tangent of theta is y over x? Well, let's see, y is 2 and x is 0. What about that? That's undefined, isn't it? So we can't use this to think about our angle, but what we can do is think about our graph. If I graph the ordered pair 0, 2, I have a vector running up on the y-axis, if you will. So how do I get from here to here? What is that angle? It's 90 degrees, isn't it? Recall that the tangent of 90 degrees is undefined, isn't it? So that does make sense. So the 2i in trig form, my r was 2, CIS 90 degrees. Okay, convert negative 3 plus 3i from standard to trig form. Our ordered pair is negative 3, 3. R is the square root of x squared plus y squared. So for this problem, of course, x squared is 9, so is y squared. 9 plus 9 is 18. The square root of 18, I'm going to think about 2 times 9. Of course, we can take the square root of the 9 and get a 3, so 3 square root 2 is r. The tangent of angle theta is y over x. So for our problem here, the tangent is 3 over negative 3, which gives me a negative 1. Okay? Now, let's be careful about thinking about this angle theta. I always encourage you to either actually graph the complex number or think about what the graph would do. If I graph this ordered pair, negative 3, 3, negative 3, 3 is going to put me where? In the second quadrant. So I know that this angle theta is a quadrant 2 angle. Now, think about what angle has a tangent of 1. 45 degrees does, doesn't it? So my reference angle is 45 degrees, but I want it over here in quadrant 2. So if I have 180 minus 45 as my reference, that leaves me what? 135 degrees is my second quadrant angle, whose tangent then is negative 1. So negative 3 plus 3i is my r value, which was 3 square root 2. cosine plus I sine theta, theta is 135 degrees, and we have the trig form. Now in this next example, we're going to have to use our calculator. Convert 7 minus 2i from standard to trig form. What's our ordered pair? It's 7, negative 2, isn't it? Okay, so r square root x squared plus y squared. Let's see, if I square x, I have 49. If I square y, I get 4. So that's what, the square root of 53, isn't it? I don't believe we can simplify the square root of 53, not that I can think of. Now, before we do this angle thing, let's look at a graph. If you graph 7, negative 2, where are you going to be? 7, negative 2 is going to put you down here in quadrant 4. So we want to remember that. Now, we do know that the tangent of theta is y over x. So the tangent of theta is negative 2 over 7. Now, how are we going to find this quadrant 4 angle? Well, this is not a value that gives us a special angle, is it? So we're going to go to our calculator and we're going to find a reference angle from the calculator that we can then use to get our value. Now, let's be sure we're set for degrees because we've been giving these answers in degrees. So what I'm going to do first, and I'm going to think about how do I get this angle, I'll have to use an inverse tangent. We know the tangent is negative 2/7. So the inverse tangent of negative 2/7, and you may need to use a parenthesis there if you're dividing that out. I'm going to write down here that I have a reference of negative 15.95. Let's see, I think what I'm going to do here is round this off to negative 16 degrees. Okay, so I have a reference of negative 16. Now that's telling me it's 16 degrees coming down this direction. Recall that it said theta is generally given as an angle between 0 and 360. So what we need to do is figure out what's the angle coming around here. And of course, to get that, we just need to subtract that 16 degrees from 360, and theta is approximately 344 degrees. Okay? So 7 minus 2i in trig form. R was the square root of 53. Cosine plus I sine, our angle is approximately 344 degrees. Let me change that sort of a wavy equal, because that's not exact, but that's pretty close. Now, you may want to keep more decimal places in this angle. I will say this, you can always find the exact value of R because of this formula. But with theta, when you have to go to your calculator, you are going to have to do some rounding off. And again, I caution you, when you're using your calculator, or even when you have special angles, pay attention to your quadrant so that you get the correct angle for that trig form. Okay, I have one other example I want us to look at here. Convert negative 5 minus 3i from standard to trig form. Okay, our ordered pair would be negative 5, negative 3. So r is the square root of x squared plus y squared. Alright, so if I square x, I get what, 25? And if I square y, I get 9. That gives me the square root of 34. Let's see, 2 times 17. No, we can't reduce that, so we'll just leave it the square root of 34. Now, we know that the tangent of theta is y over x. So we have that the tangent of theta is negative 3 over negative 5. Notice that becomes positive 3/5, doesn't it? Okay? But again, because that's not a special value, we're going to have to go to the calculator. But let's think about the quadrant. Where will we be if we graph negative 5, negative 3? We're going to be where? In quadrant 3. Recall that the tangent in quadrant 3 is positive. but we want to be sure that we get the angle that comes all the way around here. Now let's go to the calculator. We're going to have to use an inverse tangent on our calculator of 3/5. And again, you may need parentheses if you're dividing 3 by 5 there to get that. You're doing the inverse tangent of 0.6. Keep that in mind. So again, I'm going to say I have a reference of about 31 degrees. Now it's like 30.9637. Again, you may want to follow instructions from your instructor on how many decimal places to keep here. I'm just going to round off to degrees, so about 31 degrees. That reference angle is going to tell me that this is 31 degrees here, okay? The 31 degrees in the first quadrant, reference over here, so I've got 180 plus 31 to get my angle. So let's see, 180 plus 31 is what? 211, I believe is correct. Okay, so let's write the trig form. -5 minus 3i is approximately the square root of 34 cosine plus I sine 211 degrees. This completes the lesson on converting from standard form to trig form or trig form back to standard form. You might be wondering, why are we doing this? Well, you'll find if you follow in subsequent lessons, we're going to learn how to multiply and divide complex numbers when they're in their trig form. And you'll find that as you compare that to the way you multiply and divide in the algebraic or standard form, that sometimes it's much easier in the trig form. We're also going to look at how to find cube roots, square roots, fifth roots, and that sort of thing of complex numbers, which is basically impossible almost unless you go to the trig form. So this completes this lesson, and I hope that you find that it helps you very much in your studies.